Hello, this is CS470, in which we will discuss about learning. So this chapter covers learning. The first part of this chapter is about data, and this is similar to the second chapter of the elective course CS466. So if you're taking it, you will notice the overlap between this part and that chapter. After that, we will discuss about the main paradigms of learning, and then we will cover some well-known algorithms. So let's get started. This is the outline of our class for today. We will discuss about large-scale data, and then we will define what is data, or what do we mean by data. Then we will discuss about different kinds of attributes that is used to describe objects, how objects are different in types, how can we improve data quality, and how to measure similarities between objects or data objects. First point, large-scale data. We are living in an era that is called big data era, where there has been enormous amount of data generation, both in the commercial and scientific databases, and this is due to the technologies that have been developed. For example, in the biomedical domain, nowadays throughput technologies can produce terabytes of data in a matter of hours, and that was not possible 1 or 2 decades ago. So how can we make use of such data to, for example, predict the outcomes of the disease, find treatment, or avoid getting infected with some viruses? So the idea is to gather such data. For example, in the scientific field, you have an idea of what to do with this data. You have a question that you want to answer, but sometimes even for a purpose that is not envisioned, that is not stated in advance, you can generate this data for future use. So the data will be useful anytime, in any form. So commercially, giant companies like Google, Facebook, Yahoo, and Amazon generate this data and use it to improve their services. For example, Google use it to improve their search. Facebook use it to improve image recognition of faces. Yahoo use it to promote its the websites that it's hosting, and also to improve search. Amazon use it to improve recommendation, or to improve product recommendation for books or any other gadgets. Also, in several scientific disciplines, data is being used or generated at enormous speed. For example, NASA archives over petabytes of Earth science per year. Telescopes scanning the skies also store or generate sky survey data. And if you are familiar, there was an image of a black hole that was constructed, I think, 1 year ago, more than 1 year ago, and that image actually was constructed by machine learning techniques, and by using thousands of images or sky images, and collecting them. First collecting them and then applying machine learning techniques to construct the final image of the black hole. Also, in the biomedical domain, the gene expression data, or the high throughput technologies generate data that are related to diseases or chemical compounds that can be used to find cure or to find therapy for such diseases. Scientific simulation in the area of geography and weather forecast generate also a large amount of data that are being used to predict the weather outcomes or predict the events of tornadoes or storms. So employing machine learning or data mining can help scientists in automating the process of analyzing such massive data sets, and also help them in generating hypotheses and testing this hypothesis without having to actually, for example, wait or do the actual experiments. For example, in the gene expression data, or that predicts the outcomes of using several drugs without actually having to take this drug and applying it to every sample. So by using purely computational techniques, we can generate and test our hypothesis. So what is data? Data is a collection of data objects and their attributes. An attribute, also called a feature, is a property or characteristic of an object. So here on the right we have a table that consists of a number of rows and a number of columns. The number of rows are the data objects, the data samples or the data points, and the columns represent attributes. So these attributes are used to describe every data object, and the last attribute is sometimes used to give the outcome or the label of every data point. So an example of such of attributes are eye color of a person, temperature, and this table is the refund, and this is considered a binary attribute because it has yes or no values. Marital status, which can have also here in this case 3 different values, and by this is considered a categorical one because it can have different categories or different values. An income, which can be a numeric value, which can have numeric values, and then the class label, which in this case is a binary class label. So an attribute or a feature is also known as a variable, field, characteristic, or a feature. A collection of attributes describes an object or a sample, as we said, and also a data object is known as a record, data records, points, case, sample, entity, or instance. So what kinds of attributes that can be used to describe objects? So we have several types of attributes. We have nominal attributes. In nominal attributes, we differentiate objects based on names. So the value of a nominal attribute are symbols or names of things. Each value represents some kind of category, code, or state. Nominal attributes are also referred to as categorical. So in our previous example here, the marital status is categorical attribute. In computer science, we sometimes refer to these as enumeration. Examples of such nominal attributes are IDs. So IDs represent distinguished objects. Although these are numbers, they are used to to represent persons or to represent items. So ID represent items. So they are the numeric name. You could consider it as a numeric name or numeric identity of an item or a person. Eye color, zip codes, marital status, all of these are examples of nominal attributes. So what are the properties of nominal attributes? First of all, their values do not have any meaningful order. So we cannot actually order the data samples based on, for example, ID. Well, ID is a unique identifier. It doesn't follow any order. Similar to eye color or zip code or marital status, they don't follow any order. And what does that mean? Can we compute averages? Can you compute average of a number of ID numbers, for example? No, we cannot do that. We cannot find the middle element because we cannot order them. But we can find the mode or the most occurring item value. So, for example, if we have a collection of data that represent people with their eye color, so we can see within this collection of persons or people how many people have, for example, brown eye color or black eye color. So if we want to find the mode of such data, we find the value that is most occurring. For example, let's say the black eye color is the most occurring value of such attribute, and therefore we can find the mode. So also such data, they cannot be used quantitatively, so we cannot add or subtract. We cannot apply mathematical operations such as subtraction, division, and multiplication on such data. We cannot add ID numbers because they are used to identify persons or items. We cannot add them or apply any other mathematical operations on them. One thing to note about nominal types of attribute is that because they represent symbols or names, or they could represent categorical values, they can then be assigned codes like 0, 1, 2 to refer to these categories. Also, another type of data is type of data attributes is a binary attribute, which is you could think of it as a type of as a nominal attribute, but having only two categorical values, which is yes or no, 0 or 1, on or off, and so on. So it's a Boolean type of value. So several examples of that. You can think about some of these examples. Properties of binary attribute. A binary attribute is symmetric if both of its states are equally valuable and carry the same weight. So there is no preference on which outcome should be encoded as 0 and 1, and this applies to, for example, to attributes such as gender, where you don't have any preference. I mean, the gender, whether it's a male or female, they can be encoded as 0 or 1. If male can take 0, female can take 1, and vice versa. But for example, to refer to diseases, and this is conventional. So to refer to the outcome of a state or the outcome of a disease or a virus, we give more weight if the output is positive, because this is more we are interested in knowing if it's positive or not, and therefore the outcome of a medical test For example, for COVID-19, by convention we encode the most important outcome, which is usually the rarest one by one. So we are interested in knowing whether a patient has a COVID-19 or not, and therefore we encode the him or her having having that attribute value as 1, positive as 1, and the other by 0. So COVID-19 negative would be assigned 0. This is by convention, but it can also work the other way around. Another type of attribute is ordinal attribute, which allows rank or order, but not the actual degree or magnitude of difference between them. For example, a grade, military rank, size, customer satisfaction ratings, and so on. So the properties of such attribute is that they describe order, not magnitude. They can be obtained from discretization of numeric quantities. For example, if you are referring to the size of an item in kilograms, and you could and you have the size from 0 to 100, you could refer to the size from 0 to 20 as small, from 20 to 60 as for example medium, and above 60 it could be for example large or big. Similarly to the grades that are below 60 can be considered F, above 60 in the range from 60 to 69 as for example D and C, and then B and A, and so on. However, when it comes to the measures of central tendency, like applying the mean, mode, or median, we can only apply the mode and the median to ordinal types of attributes. You can find the middle element in an ordered sequence. You can say, for example, you can order the elements from small to medium to large or big, but you cannot define a mean on the ordered list or the ordinal type of attributes. As we said before, with regard to nominal attributes, including binary and ordinal attributes, they are used to represent qualitative data types. That is, they can represent symbols or categories, but they cannot describe feature in terms of the actual size or quantity. So as we said before, with regard to nominal and including binary and ordinal attributes, they are qualitative. That is, they describe a feature of an object without giving an actual size or quantity. So the values of such qualitative attributes are typically words or symbols representing categories or ID numbers, and so on. Another type of attribute is a numeric attribute, which is quantitative. That is, it is a measurable quantity, and this is unlike the previous types of attributes, which are nominal and ordinal, in which we said they are only qualitative types of attributes. These types of attributes, numeric attribute, can be represented in integer or real values. Numeric attributes can be either interval scaled or ratio scaled. Interval scaled attributes are measured on a scale of equal size units. The values of interval scaled attributes have an order, and can be either positive, 0, or negative. Thus, in addition to providing a ranking of values, such attributes allow us to compare and quantify the difference between values. And this is one of the important properties that distinguish this type of attribute from the previous types of attributes, which are only qualitative. Examples of such attributes are the temperature, either in Celsius or Fahrenheit, calendar dates. So you can have a ranking of temperature values. You can also rank calendar dates from the old calendar dates to new calendar dates. And in terms of temperature, you can order them from smallest to largest, or vice versa, and so on. Properties of interval. Sorry, there is a typo here. Properties of interval scaled attributes are that they do not have a true 0 point. And what does that mean? And this means for such attributes, an absolute 0 does not exist. For example, the temperature in Celsius and Fahrenheit, we cannot say that the 0 represents the case in which there is no temperature. And this makes it difficult or impossible to represent these attributes or the values of these attributes as multiples of each others. So for example, we cannot say that 10 Celsius is twice as warm compared to 5 Celsius, for example. In other words, the absence of a true 0 point does not allow us to represent the values of these attributes as ratios. And for that reason, we will find out that the ratio scaled numeric attribute does actually allow us to do that. The values of such attributes have a true 0 point, and therefore they allow us to represent things as multiples or as ratios. We will come to that in the next slide. Now, also another property of interval scaled attribute is that we can apply all measures of the tendency, such as finding the mean, finding the median, and finding the mode of such values. On the other hand, ratio scaled attribute is a numeric attribute with an inherent true 0 point. So there exists a true 0 point of such values, and so if that is, if a measurement is ratio scaled, we can speak of its values as being multiple or ratio of another value. In addition, the values are ordered, and we can also compute the difference between values as well as all measures of central tendency, such as mean, median, and mode. For example, with regard to representing multiples and ratio, now, unlike what we mentioned about representing temperature in Celsius and Fahrenheit in the previous slide, the Kelvin temperature does have a true 0 point, and this occurs at a degree that is equal to minus 273.15 Celsius, and it is the point where particles that comprise a matter have zero kinetic energy. And for that reason, we can represent the Kelvin temperature as a ratio. Also, the count and examples of such attributes is attributes that has counts, for example, years of experience, weight, height, and so on. What we also want to cover in this lecture is how data are different in types. So we will cover these types of data, and we will refer them, we will categorize them first in terms of the data being can be represented as a record data, or as a graph data, or as a ordered data. type of data. Record data is data matrix, document data, transaction data. Graph data can be social networks, protein-protein interaction networks. Order data can be spatial data, temporal data, and sequential data. For example, with regard to record data, such data consists of a collection of records, each of which consists of a fixed set of attributes. So a data matrix, similar to this one here, can be thought of as points in a multi-dimensional space where you have the point and each feature represent a dimension. So this data set can be represented by an n by m matrix, where n is the number of rows and m is the number of features or dimensions. While document type of data are commonly used to represent text-based data. So in such data we have each document represent or becomes a term vector. We call it a term vector. Each term is a component attribute of the vector. For example, document 1 we have has a number of for example, paragraphs, and we count. We have a dictionary. So this dimension, the number of columns, represent the number of words in our dictionary, and each document we count the number of words that belongs to this. For example, in this document we have team being repeated 3 times, coach 0 time, play 5 times, and so on. So we give the count of these words that in our dictionary that is found in our document. Similarly, we do that for all of the documents that we have. So the value of each component is the number of times the corresponding term occurs in the document. And this type of representation or encoding is called a bag of words. And this is a very well-known representation of text data, of the way we encode text data. One of the drawbacks of such representation is that it gives you the absolute count of such words in documents, but it doesn't give you an idea of how these words are being ordered, or what is the sequence of the so it doesn't give them information about the sequence of appearance of such words. So it's only the number of occurrences of such words in the respective documents. Transaction data, it's also another type of record data, where each record represents a transaction and involves a set of items. For example, consider a grocery store. The set of products purchased by a customer during one shopping trip constitute a transaction, while the individual products that were purchased are the items. For example, we have here one transaction that is a result of a customer going to the supermarket and buying these items. So this is one transaction, this is another transaction, third transaction, and so on. So the first transaction contains of items such as bread, coke, and milk. So these items might appear more frequently than other items, for example, together within one transaction, and it could this pattern could reoccur in other transactions as well. Graph data is data that can be represented in a form of a graph or a network, where you have a number of nodes connected by edges, and this is an example of such networks is social network, Twitter, Facebook, where you have, for example, in Facebook you have the nodes as being for example, the Facebook users, and then each Facebook user has a number of friends, and they are connected with each other. Friends are connected to other friends, and a network can be formed out of that. Similarly to Twitter, Instagram, or other social networks. Also, in terms of biological data, we have protein-protein interaction networks, where we have the nodes representing the proteins, and the edges representing their interactions. Yeah, here is the example. So we have a number of proteins, and they involve a lot of interactions between these proteins, and by clustering that, by finding out which proteins interact with each other more, and you can see that if you see that some proteins interact with each other more than other proteins, you can derive some hypothesis. You can say that these proteins might be involved in the same mechanism, or they might be involved in the same disease. And with that, you can derive new facts or a new insight. Also, for ordered data, we can have where we care about the order of points, and this applies to spatial data, for example, with regard to geographical locations. Another type of ordered data is another example of ordered data is genomic sequence data. And in genomic sequences, you can have the chromosomes that actually make up the DNA of the human being. For example, the order of these amino acids, these are called amino acids, matter because we as humans have some variations that represent that makes us different from each other, and those variations are actually a result of some differences between the location of such amino acids in the long sequence of the human DNA. So studying these differences, or what they call mutation, help us find information about traits like hair color, height, weight. Also, an important thing is finding about diseases, or for example, so with regard to diseases, if we have if there is so with regard to diseases, if there is a mutation, or if there is a difference in the order, whether it's insertion, deletion of these amino acids, it could mean that such person or such patient can have more susceptibility to a certain disease than other patients who does not have this amino acid insertion or deletion, who does not have this variance or difference in his or her amino acids or the DNA. So studying these types of ordered data gives more insight about how to treat these diseases, and how to develop the drugs that can help treating these diseases. Also, another example of ordered data is the data that relies on the time. So such data is called temporal data, and a famous example, or a well-known example for that, is the stock market. So here we have a data that is that can be represented with the time being one of our main dimension, and then we study the price predictions over time for some companies, and this can help investors see which companies are more promising than others. But of course, it's hard to find out which companies are more successful than others, because in terms of stock markets, there are so many other factors that can play, or unpredictable factors that can play an important role into predicting the behavior of the curve. So now that we have studied about what is data, what kinds of attributes that can be used to describe data objects, how data are different in types, it's time to see if we can use these data just directly, raw data, or is it necessary to improve the data quality. You'll find out that using the data as it is, like using the raw data, does not actually help much if you want to learn or if you want to apply machine learning, because the data in its raw format are usually full of noise, and they need to be pre-processed. So in the following slides, we will learn about simple techniques to improve the data in order to make it ready for learning. Before that, we can see an example of how such poor data or unclean data or unprocessed data can affect the classification model. For example, let's say we have a classification model for detecting people who are loan risks, and that model is built using poor data. Such model would actually make some creditworthy candidates deny the loans because it's built on poor data, incomplete, has missing information, and so on. While more loans can be given to individuals who default, who do not pay back. But here, these three questions: what kinds of data quality problems? How can we detect problems with data? And what can we do about these problems? So, examples of data quality problems are noise and outliers, missing values, duplicate data, wrong data, or fake data. So in terms of noise, for an object, noise is an extraneous object. So for attributes, noise can refer to modifications of original values. Also, another problem of data is outliers. So outliers are data objects with characteristics that are considerably different than most of the other data objects. For example, here you can see this cluster, and you can see one point here. That means this point, and this point can be considered as outliers. And we can study outliers in two cases. We can study outliers as noise, and we want to remove them. So in the other case, our target of studying outliers would be, for example, to find out whether some credit card fraud happens or not. By finding out a scenario for that would be to check out the places where this the payment of this credit card has happened, and by detecting places that for example the customer does not usually go to, for example withdrawing money from a place that is very far away from the place where he usually uses the card at, would be so that these places represent outliers, and we want to study them. So what could be the reasons of such occurrence of outliers in a data set? It could be the way that how the data is being collected. For example, if the data is being collected by an instrument, or there could be some defects with this instrument. For example, a common defect is in the way that genomic data, such as the sequences the genomic sequences or the DNA that we discussed earlier. the instruments that are being used to generate those DNA long sequences can insert some artifacts into the data, and it's important to do some pre-processing to remove these artifacts. Also, a data could be entered wrongly, for example. There could be also some problem related to data transmission or the technology limitation. For example, if the data is being entered as they arrive to a specific system, then some data might be entered before other data, and this will cause distortion in the output, in the final output. In terms of missing values, there are several reasons of missing values. So, for example, the information is not being collected, so people may decline to give their age, weight, or financial related information. Also, attributes may not be applicable to all cases. For example, the annual income is not applicable to children. And the way to handle missing values is to, or even outliers, is to either eliminate the data objects or variables that have the missing values or the outliers, estimate the missing values by ways of finding the mean, the median. So if it's numeric values, we can find the mean of such values. We can find the median to represent the values that is missing. Another way of handling missing value problems is to ignore the missing value altogether during analysis, so we don't consider them, or replace values by their probabilities. And there are several techniques that can be used to find out the most probable value to do. So we can use regression to actually replace missing values. That is called data imputation. So we can impute the values by finding or by using regression, or by using induction trees, or induction, using decision trees. And there are other techniques such as matrix multiplication. It's beyond the scope of this class, but there are several techniques to replace missing values, and probably this is one of the techniques that is most reliable because it replaces the missing values by the most probable value using yet another machine learning technique such as regression or decision trees. Another problem with data is having duplicate data. So the data set may include data objects that are duplicates or the same as or almost the same as other data records. So this is a major issue when we merge data from different resources. So data could be referred to with using different terms, but they actually mean the same thing. For example, names of cities. In some source or some data source, you could refer to a city by its full name, or the data could use the full name to represent the city, while in another source or data source, they could use the initials. For example, you could use JIC, for example, to represent the Jubail Industrial City, while in the other source they use Jubail Industrial City, the full name. And when you merge these data from different resources, the computer will understand it as two different data, or the algorithm could understand it as two different data, but they are actually the same data, so they need to be replaced by the same ID, the same name, or the same ID. So this is one of the major issues that needs to be fixed before before applying machine learning techniques. Also using different units. For example, in one database, the units to represent distances could be miles, and another database could be kilometers. So such unification of values should be applied. The knowledge engineer or the data scientist or the machine learning expert should apply some data pre-processing steps to fix. In data cleaning, we deal with duplicated values by unifying the underlying objects that these values refer to. For example, we can unify the measurement units to be kg instead of kg, or ounces or other types of units when we merge them from different heterogeneous data sources. We can also fix the abbreviation so that the underlying data objects refer to the same thing. So if we are using abbreviation of cities or addresses, we need to make sure that this abbreviation is the same across the different data sources. Also in this lecture, I would like to mention about this techniques for pre-processing, which is called normalization technique. So normalization ensures that attributes are on the same level of measurements, and this is very important before applying any machine learning algorithm. For example, let's see this data matrix where we have heights that range from 1.5 to 2 meters, and weights that are normally above 40 or but above 45 kg for different people. So a common technique to do is to normalize these values to make them at the same range, so that when you use the machine learning algorithm, these attributes do not dominate one another, and therefore they will not affect the classifier or the machine learning algorithm during the learning phase. Min-max normalization, which makes the data to range between 0 and 1. So the height data values will be from 0 and 1, and the weight as well. So when we apply it, we need to apply it across all columns or across all attribute or feature values. And the way to apply this is to find the min for a specific attribute, the min value across the whole column and the max value across the whole column, and then subtract the min from and divide by the difference between the max and the min for each value in this column. And what you would get is you would get a value between 0 and 1 for the height, and similarly if you apply it on the weight. Another technique of normalization is Z-score normalization, which finds the mean of certain feature values, find the standard deviation of the same feature value, and then subtract the mean and divide by the standard deviation for all of the values of certain attribute. The normalization is sometimes called scaling or standardization, because we are scaling the data to be to have the same scale, so that the feature values of every attribute have the same scale and do not or dominate each other. It's also important to note that normalization can be referred to as standardization or scaling, because here we are ensuring that feature values are at the same scale so that no feature value can dominate the other feature or attribute by having a drastically smaller or drastically larger values between one another. The last point to discuss in this lecture is measuring similarities between data objects, and this is also important along with normalization. It's important as a pre-processing or as a way to improve as a pre-processing step. Another technique to improve data quality and also to serve as a pre-processing step is normalization. And it's important to note that normalization can be referred to as scaling or standardization. The last thing to cover in this lecture is how to measure similarities between objects, and this is one of the techniques to pre-process data. The last thing we want to cover in this lecture is measuring data similarities or measuring similarities between data objects. This may not be a very essential technique to improve the data quality itself, but it could help produce better output if the algorithms is set to use similarities between objects instead of the object themselves. There are several studies and works that actually depends on using the similarity measures instead of the actual feature values. So I included this in this lecture as a way to improve the outcome of the learning algorithm or machine learning algorithm. So what do we mean by similarity? So similarity is a numerical measure of how alike two data objects are, higher when objects are more alike, and the value of the similarity falls between 0 and 1, where 0 means there is no similarity at all, and 1 there is the two objects are identical, or the two data objects are alike. The dissimilarity represents the distance, and it is a numerical value of how different two data objects are. Lower when objects are more alike, so the distance between two data objects is 0, and when the two objects are alike, so it's the opposite of similarity. Similarities between identical objects are 1. Distance between identical objects is 0. So we will cover the Euclidean distance, and as we know, the Euclidean distance measures the distance between 2 points in the Euclidean space. So the difference between two data points or data objects, the Euclidean space, where we don't have only 2 dimensions, we can have m dimensions, can be defined as follows. So this is a generalization of the 2D Euclidean space, where here we don't have where here m is not 2, but it could be any number. It could be 100 or thousands. Also, a standardization, scaling, or normalization, as we defined earlier, is necessary if the scales of the attributes are different. So if one attribute can be measured in hundreds, where the other attributes is measured in tens or even below that. So this is an example. Let's say that we have these points. Here we have 4 points represented in the 2D space. So the data matrix in this case is a 2 by d 2. It's a n by n, where n is the number of points, n by n matrix. The diagonal the diagonal represents the similarity between the data object and itself, and it will always be 0. Not the similarity, sorry, the distance. And the distance here, because they are identical, the distance is 0. And we see that we only need the upper triangle of this matrix, because the lower triangle is the same. The distance between P and 2 is the same as the distance between P2 and the distance between P1 and P2 is the same as the distance between P2 and B1. So we can only consider, if we were to save these values, we can save only the upper triangle. Another measure of similarity is the cosine similarity, and the cosine similarity is famously used with two document vectors. So you remember what we discussed in this lecture about document vectors representing text in the bag of word model, where we have a number of documents, and we have the dimensions or the attributes representing the terms, and the values represent of this matrix represent how many times this term occurs in a specific document. So you may refer to the slide. So this is the cosine similarity can be used to measure the similarity between document 1 and document 2 by taking the dot product, with cosine similarity between these two data term vectors or feature vector. So the cosine similarity is defined as the dot product between the two vector, or the inner product, over the magnitude of the two vectors. And this is an example of how to compute the cosine similarity. So as a summary of this lecture, we covered what is data, what kinds of attributes that can describe data objects, how data are different in types, or what are the different types of data, how can we improve the data quality, and how can we measure the similarities between objects. It's worth to remind you that this is the first lecture of the machine learning part of Introduction to AI, where in this part we will just give you a small and brief introduction about data, and then in the subsequent parts we will discuss about main paradigms of machine learning, and we will cover some few algorithms.